In this lesson, we are going to talk about pointers and multi-dimensional arrays. As we have seen in our previous lessons, the concepts of pointers and arrays go together. We have already talked about pointers in context of one-dimensional arrays, how we can work with one-dimensional arrays using pointers. Now let's see how we can work with a two-dimensional array or a three-dimensional array or a multi-dimensional array in general using pointers. To understand this concept, once again, we first need to understand how multi-dimensional arrays are organized in computer's memory. Let's first go back to the organization of one-dimensional arrays in memory. When we declare a one-dimensional array, something like this, let's say we are declaring an integer array A of 5 elements, then basically what we are doing is we are creating 5 different integer variables that we can name A0, A1, A2, A3 and A4 as one contiguous block of memory. What I'm showing here is a section of computer's memory. Array A, let's say, is stored in this section of memory, and the starting address of A is 200. As we know, each byte in a computer's memory has an address, and if we assume that an integer is stored in 4 bytes, which is what it takes in a typical compiler, then the block of 4 bytes starting address 200 will be A0, as I'm showing here. Block of 4 bytes starting address 204 will be A1. Next block of 4 bytes starting address 208 will be A2, and so on. I'll fill in some values here. We had seen this earlier also in our previous lessons. If we write a statement like this, then this is all right. If I just use the variable name A, then name of the array in an expression basically returns a pointer to the first element of the array. Because this is an array of integers, so each element will be an integer. Hence, A returns a pointer to integer. Once I have written a statement like int asterisk p equal a, I can use pointer arithmetic and dereferencing to access all the elements in the array. If I would just try to print the address stored in p, and I'm not using full printf statement here, my output will be 200. If I would simply try to dereference p, then output will be 2. If I would try to print something like asterisk p plus 2, then output will be 6. Because we have an integer pointer, adding 1 will take us to the address of the next integer, which will be 4 bytes ahead. Adding 2 will take us to the address of next to next, which will be 8 bytes ahead. If we would be printing p plus 2, it will be 208, and if we would dereference and we would print asterisk p plus 2, then it will be value 6. We have already discussed pointer arithmetic in our previous lessons. Now language gives us this flexibility that we can use the name of the array just like a pointer for all the dereferencing. So instead of doing all of this printing with p, if we would do all of this with a, it will still be the same. In fact, asterisk a plus I is same as ai. These are alternate syntax, and a plus I is same as ampersand ai. Both will give us the address of the ith element in the array. Please remember that even though we can use the name of the array just like pointer for all this dereferencing and arithmetic, it's not same as a pointer variable. So we can do something like p equal a, like what we have done here. So this is all right, but we cannot do the other way. We cannot say a equal p. This will give you compilation error. So this is pretty much how we would use pointers with one-dimensional arrays. Let's now say we want to create a two-dimensional array. I will declare a two-dimensional array of integers named p, something like this. Now what we are doing here is we are creating array of array. We are creating two one-dimensional arrays of 3 elements each. This time b0 and b1 are both one-dimensional arrays of 3 integers each. A one-dimensional array of 3 integers would be 12 bytes if each integer is 4 bytes in size. So if I have to show this in memory, the first block of 12 bytes starting address 400 will be b0, and the next block of 12 bytes starting address 412 will be b1. As we had said, name of the array returns a pointer to the first element in the array. This time each element is not an integer. Each element is a one-dimensional array of 3 integers. So if I would write a statement like this, int asterisk p equal b, then this will give me a compilation error, because b will return a pointer to 1D array of 3 integers and not just a pointer to integer. The type of a pointer matters not when you have to read the address. It matters when you dereference or when you perform pointer arithmetic. It's really important that we understand this. We can define a pointer to 1D array of 3 integers like this. And now if I'll equate this with p, this is alright. Equate b with p. This time if I would print just p, which is same as printing address of b0, this will be 400. If I will print asterisk p, which will be same as b0, then b0 this time is variable name for a one-dimensional array of 3 integers. So just using the name b0 will return us pointer to the first integer in b0, which will be accessed as b00. So I'm putting this ampersand sign here in front of b00. First integer in b0 will be this block of 4 bytes. Its address once again is 400. Okay, now I have also created 3 blocks of 4 bytes each in both b0 and b1, and also filled in some values. Now I'm going to write some print statements and I want you to guess the output. What will be the output if I'll try to print b plus 1? I will write the address of each block of 4 bytes in the 2D array. The address of a block is the address of the first byte in the block. Okay, so what will be the value of b plus 1? B this time is returning us a pointer to one-dimensional array of 3 integers. So if I would do a pointer arithmetic like adding plus 1, we are moving to the next 1D array of 3 integers. So we will be moving to address 400 plus size of one-dimensional array of 3 integers in bytes. So output will be 412, which makes sense because b plus 1 is same as ampersand b1 or address of b1, and address of b1 is 412. Okay, now what if I print asterisk b plus 1? When we are putting an asterisk signs, when we are trying to dereference, this is when the type of pointer becomes important. B is a pointer to one-dimensional array of 3 integers. So b plus 1 is also a pointer to one-dimensional array of 3 integers. And when we will dereference, we will get this whole one-dimensional array of 3 integers starting address 412. Asterisk b plus 1 is same as b1. So we will get b1. Now printing b1 means using the name of this one-dimensional array b1, which should return us the pointer to the first integer in b1. So asterisk b plus 1 is basically pointer to this integer at address 412. Once again, this output will be 412. All these expressions, asterisk b plus 1 or b1 or ampersand b1 0, are returning us pointer to integer. Okay, now you need to gear up because I'm going to give you some tough ones to decode. What will be the output if I will print asterisk b plus 1 plus 2? Take some time and think about it. Asterisk b plus 1, as we saw above, will return an integer pointer to first integer in b1, to the integer at address 412. Adding 2 here is performing pointer arithmetic because asterisk b plus 1 is a pointer to integer storing this address 412. Adding 2 is basically going to the address of next to next integer, which will mean skipping 8 bytes and going to reference integer at address 420. Asterisk b plus 1 in this expression can be written as b1, simply b1, because they are substitutes for each other, they are alternate syntax. So this is same as b1 plus 2, and once again these expressions are returning pointer to integer. They are returning pointer to this element b12. That's why we can also say ampersand b12. All these 3 once again are same. Let's do one more print. If you can get this one right, I can say that you're good working with 2-dimensional arrays using pointers. What will be the output for this expression, asterisk of asterisk b plus 1, what will be the output for this expression? Think about it. Whenever you encounter an expression with pointer arithmetic and dereferencing, then you must go step by step. Here, B is returning us pointer to one-dimensional array of size 3, one-dimensional array of 3 integers, and dereferencing it will give us the one-dimensional array. So asterisk B, as we know, will give us B0. Asterisk B is same as B0. Now B0 in my expression, because B0 is named for a one-dimensional array, returns me pointer to the first integer in the one-dimensional array. So B0 returns pointer to integer. We will get a pointer to this integer at address 400. Now what will happen if you will add 1 to an integer pointer? It will take you 4 bytes ahead to the next integer. It will return you pointer to the next integer. So we will get a pointer to this integer at address 404. Asterisk b plus 1 is basically ampersand b01, and with this final dereferencing we can get rid of this ampersand, so the overall expression will be b01, which is 3. For a two-dimensional array, bij, where b is name for my two-dimensional array and I and j are some indices, can be written as asterisk of bi plus j, and once again bi can be written as asterisk of b plus I. So these three expressions are same. I would recommend trying all of this in real code. So far this discussion has been about working with two-dimensional arrays using pointers. We will stop here for this lesson. In another lesson we will play with some real code, and we will also discuss how we can work with an array of further higher dimension like a three-dimensional array. We will also discuss passing of arrays to functions through pointers. This is it for this lesson. Thanks for watching.